parameters in elliptic systems.
Thank you. As also has said, that I am from the nuclear engineering department, so I am a nuclear engineer, but I am interested in mathematics. And I have a long time cooperation with Professor Carlos Alves from the Mathematics Instituto Superior Técnico at Lisbon University. And we work mainly in reconstruction of parameters, identification of parameters in inversus problems. So the talk include coefficients is very close with the cooperation with Professor Carlos Alves. The objective of the presentation is to show my ideas in this subject. I will not discuss regularization strategy because I want stress the ideas and the concepts that is involved in the methodology that I am developing. The methodology proposed will explore concepts as Lipschitz Boundary Dissection, complementary mixed problem with trial parameters, internal discrepancy fields. That is a concept that I am used to explore the fact that when we use trial parameters different from the parameters of the problem, I obtain a gap in the Calderon projector. The main techniques is variational formulation involving finite element analysis, boundary integral equation, and of course, Calderon projector. It's an engineering problem. Since I started as an assistant professor in the 70s, I work with material properties. Material properties is a central question in engineering. And the ideas can evolve from thermomechanics and from continuum mechanics, constitutive theory, to, in the most modern way, to the identification and in the area of inverse problems. Basically, we pose a mathematical problem. It's a Dirichlet domain with Lipschitz boundary. I need Lipschitz boundary because I will use Calderon ideas of extending the problem from the interior to the exterior of the border omega. And so develop the inverse theory based on the single layer and double layer potential, in this case, of equation. Basically, the source, I consider initially a system of M equation, but I will, at the end, fix in a more simple problem that I can use to elaborate examples, numerical examples. So I have the Cauchy data that I am supposing be complete at the boundary. And the problem is this. I denotate the problem P alpha is an operator, strong elliptic operator. The source, this is a matrix equation, finite number of columns, and infinite dimensional. There are fields, are H1 omega fields, continuous field. The trace operator, the Dirichlet boundary, and in this case, we have a complete set of data, and the conormal derivative. Those operators are basic for the theory. The main question with this problem is that if I can relate the Cauchy data with constitutive parameters alpha and source F. That is, if I can find some functional equations which could be solved, or at least conduct to a good framework for analysis. I will not solve the Calderon project equation because this it will be a very sophisticated implementation of boundary element method. But I will use to analyze the problem and obtain some conclusions about what I must do to complete my objectives. What are the consequences of incorrect value of parameters? What are consequences of incorrect values of Cauchy data? How the Calderon project will respond to those questions? Basically, I will have to solve and use this auxiliary mix problem that is a well-posed problem for the strong elliptic operator, and I have two boundaries. One boundary with Dirichlet data, and another boundary with Cauchy data. So is well known. The central question is, so I have excess of data at the boundary. So I can split those data, and I can create the concept of complementary problems, make a definition with complementary problems to be solved. And those complementary problems are consistent with correct values of parameters. If I use a trial parameter in order to obtain the solution or make an algorithm that will converge to the exact parameter, I will obtain an inconsistent system. And this inconsistent system will be reflected in the Calderon projector. That will be no more a projector, but will present a gap. And this gap can be used to generate a discrepancy field. I am naming as a discrepancy field inside the domain. Okay? So, first of all, the definition of complementary problem in Lipschitz domain are two problems that where one has a Dirichlet boundary, the other has a Neumann boundary. But the two problems complement the all set of Cauchy data of the inverse problems. So I have the Cauchy data, and I project the Cauchy data in the two boundaries. The same Cauchy data are shared by the two problems. So the Calderon projector is an operator in the boundary of the problem. As I say, Lipschitz boundary, you can extend, you can have an interior problem and an exterior problem, and you can formulate with fundamental solution the double lower, the single lowered potential, and take the gradient of one, the trace, and the conormal trace of the boundary, and obtain a singular integral operators that, if you know the fundamental solution, you can analyze and obtain those operators. We will suppose that we can construct this, that this fundamental solution exists. And eventually, I can, using element physics, I can construct this fundamental solution by using the spectral problem. So this is the idea. This is the main theorem and the results that in which the method was based. Basically, I say, suppose that you have two complementary mixed problems with respective solution. One, two. Independent of Cauchy data dissection, they will be equal. The proof of these results is based on Calderon projector, and can be made for the same Cauchy data, and I can use different Lipschitz dissection of the boundary. I have noted that people that do conductivity tomography use these different Lipschitz dissection frequently in as they want produce Cauchy data for reconstruction. The boundary element method usually when it is used to solve the direct problem. So they use the data at the boundary, they use the split of Calderon projector at the boundary and complement the data. So with information for one problem, they complement the data for the other, and substitute the data in this equation that we know as third green equation, the third green equation for the problem. So it's not difficult by using this kind of argument to show that the two problems that you solve using complementary data at the boundary will give the same fields in the interior of the ground. For correct value of parameter, the Calderon projector has no gap. Basically, the Lipschitz boundary dissection of the Calderon projector is an equation like this. Is this equation that I mentioned before? Is there a functional equation that can be used for solve? And we don't solve this equation, but we can use to prove this fact. This is the important consequence of the theorem, that is, for a given association of Lipschitz domain with model given by an operator L alpha, the Calderon projector is the restriction which the Cauchy data must satisfy in order to be consistent with a boundary values problem. If the inverse problem is solved with trial parameters, values different from the exact value, the associated Calderon projector will present a gap. Then the solution of complementary problems associated with Cauchy data will be different, and the internal discrepancy field is calculated. So it's a way that I can extend the discrepancy information between data at the boundary to the interior of the problem, as we will see in the next problem. This is an example of discrepancy field. I am developing a computer program, finite element computer program, in order to calculate a more flexible than the multi-field solvers. There's more even, it's more difficult to manage information to make those calculations. One is I can randomize the boundary. You can imagine that to make a Lipschitz dissection of the boundary, I have a combinatorial number of possible Lipschitz dissection. So I can produce much information about how the discrepancy propagates to interior of the solid, of the omega, to interior of the omega. I have three examples here that I chose to show to you. One is randomized, the boundary. The other is the Dirichlet-Neumann. The discrepancy produced by the two problems. One problem is Neumann, the other Dirichlet. And the others are odd even. If the node is Cauchy, it's odd. If the node is Neumann, it's even. So you see that is a field with very interesting pattern. Okay? So now I start to analyze the direct problem that I will solve and how I can manage these ideas of discrepancy fields inside the solid omega. First of all, I fix a very simple model, a model of diffusion and absorption. And this will be the operator. The three main operators are this diffusion absorption model. I forgot about reaction, convection, and the other possibility to have a very simple model to pose the ideas. The trace operator and the conormal trace operator. One in the Dirichlet boundary, the other in the Neumann boundary. And the second important equation to our formulation is the first green identity. And the first green identity has the Dirichlet functional. This Dirichlet functional that basically contains the information about the response of the system that is governed by the differential equation. If you know information about the Dirichlet functional, you probably know how to solve the problem, how to understand the problem. We have the forces, forces inside the domain omega, and you have a power in the boundary of the domain. That is a product of the conormal trace and of the function u and the trace of the function v. This is a very classical subject and can be found in books of finite elements or numerical analysis and the boundary elements method. Okay. Some comments about the Dirichlet functional that will show the importance of this concept. First of all, if U and V are functions in a normal space, then the Dirichlet functional is the energy norm. So he brings the energy that is contained in the system. If U is some Galerkin bias, or very simple Galerkin bias, in finite elements approximation with Galerkin, then phi is the stiffness matrix and absorption matrix, sum of the two. If you have another process involving the model, they will contain information about this process. They will contain information about the conductivity and about the absorption coefficient. If you use orthogonal eigenfunction in a spectral problem, then phi will be the characteristic eigenvalue. So this would be, the first one is the buckling. It has information about the geometry and about material property of the system. So, the most important of two for the inverse applications is that the inverse of the Dirichlet functional for those spectral biases gives information about the U condition of the system of the inverse coefficient problem associated with this model. This is a classical concept in inverse problems. Moderated U pose for polynomial decay, several U pose for decay. So if you have some problems, make a SVD or eigenvalue for this Dirichlet form will give a lot of information about the problem. Well, for formulate the finite elements approximation for the direct complementary problems, we have the following weak formulation. Here, we use the symmetric formulation. I have Lagrange multiplier to control the Dirichlet part of the data, and we have the Neumann data here, and this is to be solved in this framework, H minus half. Okay, so all this functional here is in the sense of duality. So I always have his way to identify this with, I am in a Hilbert space, so I have his way to identify this with a vector if he is in the dual, in the vector in the primal space. Note that those operators which start here are the extension operators. And you can use it to remove information from the boundary to the body of the problem. And not a mistake here. Here must be omega. This is this weak equation is a critical point for this Lagrangian functional. So the finite element formulation is very simple in its matrix form and can be ambient inside the MATLAB or some. Then you have a lot of recursos to deal and to a lot of algorithm and way to give solution to the finite element problem. We have degree of freedoms from vertices, from the Dirichlet boundary, from Neumann boundary, and number of parameters. So if I have a field of discrepancy inside the region omega, I can compare the two, and I will expect that it can be minimized in some sense in order to, when the discrepancy is 0 or close to 0, we'll give a solution will give information about the parameter or a close value to the parameter. So the problem is, in the guess of parameters, in some intervals, to find a parameter alpha that minimizes the complementary solution for all Cauchy data and our respective Lipschitz dissection solution. So I have the Cauchy data, that is the base information, the model, and I can use Lipschitz dissection based on the geometry of the problem and a combinatorial number of Lipschitz dissection, and I can produce a lot of information about the interior, probably information about sensitivity or to the parameters or so. Some aspects, some immediate results about the discrepancy field. If I denote by HL alpha the set of L harmonic function, is a subset of H1, when L alpha is the Laplacian, this is the set of harmonic function that you use a lot for source reconstruction problem. the first property is that the discrepancy field associates with a wrong parameter, and an exact parameter alpha is L alpha harmonic. And based on this, you can use the second, is a regular solution to the homogeneous problem, and I can use the second green identity to write a reciprocity gap equation based on the discrepancy. Of course, when we have only source problem, we usually use the set of harmonic function to the complete set of harmonic function to test the problem and solve it, and use this to solve source problem. But in this case, the advantage is not so good because I have another terms here involving the unknown part of the parameters. And of course, it is better to test for a large set, the set of L alpha zero harmonic function, than only for the discrepancy function. But this is a result. The second important result is the variational method for discrepancy field. Of course, discrepancy fields has no interior source, has only source at the boundary. That is given by this trace, conormal trace here. In the self-adjoint model here, I can exchange the conormal trace with the trace, and we'll give the same result. But I prefer put in this way. So this is an equation that not here. The parameter of alpha 0 is not equal the parameter here of the inverse problem. So for all test function in H1, for all Lipschitz boundary dissection, if for all Cauchy datum, I have this equation. Not that this parameter here of the discrepancy is different from the parameter in the Dirichlet functional. So it's a variational formulation for the discrepancy field. I didn't explore completely yet those results. And the second important result is when I evaluate the Dirichlet functional, the Dirichlet functional here for a base function VI, a discrete base function of the galactic approximation, that is in H1, 0, that is in the interior of the body. So I obtain this basic fact that the value of the functional, Dirichlet functional, concentrates inside, outside. This first 80 degree of the freedom is in the boundary. From 81 to the end is in the interior. So the information is basically concentrated at the boundary, as is expected, of course. So I can say that I have an annihilator, is a null set in the dual space. For Cauchy data consistent with parameter alpha and discrepancy fields between complementary problem calculated with trial parameter alpha 0 and Lipschitz boundary dissection indexed per LD, the Dirichlet functional, this Dirichlet functional, which has this representation, is equal to 0 for all test function in H1, 0. This is a null set in the dual space. And this can be used to obtain representation about the field, the conductive field, the fields which contain the parameters. Okay. But we can go to the brute force solution of the problem. And the brute force solution of the problem is to use some kind of quadratic functional or Bregman distance or least square or some Nelder-Mead algorithm, but based on the complementary solution, we create some discrepancy function that measure observed difference of Gaussian parameter. Norms of solution space in direct problem can adopt is this. You can construct a distance. And I construct very simple least square problem. And I didn't regularize. I can start to regularize. When I have problem with one solution, I use SVD and inspect, and the problem is very high. The SVD, the angle values, the characteristic values of singular values decay very strongly in conductive problems, in absorption problems, in this class of problems. So this is the mesh of the model, the discretized problem. This is a typical Cauchy data. I have here 5 Cauchy data. One side I put one Dirichlet data, and I have the Neumann data. Here I put 0 in all sides, and appears of a very, very common pattern for Cauchy data. I can do this for a combinatorial number of ways for all Lipschitz dissection that I can do for my problem. This is a typical parameters, least square error, least square error discrepancy. This is a typical reconstruction. And this is a conductivity. I don't know, it is a radial base, conductivity exponential, a Gaussian. And I have the exponent parameter. I have the center of the Gaussian as incongruent. I have the conductivity as incongruent, and I have the source as incongruent. I have a lot of parameters, and I use least square, and this is what the error. Of course, I have no noise in the problem. If I try to put 2 radial base function in different positions, problems with condition of the matrix, stiffness matrix, will start. And I will, of course, will be necessary to regularize. This is another graph that shows normal discrepancy versus Lipschitz dissection. I have a lot of Lipschitz dissection, and I have the norm here for P1, for P2, and for P100. And this is the, so it's very easy to calculate those things because I have optimized the software to do this. This is the discrepancy field. I remember here a problem. The first time I presented this idea was in 2013. Okay, 5 minutes. 2013. And there's a square and a rectangle inside the square. And in this rectangle, I need to identify the source, the intensity of the source, the conductivity, the absorption coefficient, and the centroid of the square, and the size of the square, 7 parameters. And I use, at this time, I was using a software console, a multi-field software, and I have so many contours. Things are much more difficult than are today. And this is the successful parameter, and the Nelder-Mead algorithm was the best because you don't need to make derivatives or or these things, and there is a very simplex algorithm, very, very robust, and the MATLAB is a good ambient to solve this class of problems. So the main result of the work is, the work is based on overprescription of Cauchy data, Lipschitz Boundary Dissection, a specialized formulation for this class of problem, finite elements, of course, a solution of multiple complementary direct mixed problem with long values of trial parameters. Of course, you have a lot of open questions to be responded. We demonstrate a theorem of complementary solution, the existence of discrepancy fields for trial with wrong parameter value, the reciprocity gap equation for discrepancy fields parameter determination, the variational method for discrepancy fields parameter determination, and an adulator that can be used to improve the a priori information about the coefficients. Okay? So I investigate numerically the methodology for linear discrepant and for with Nelder-Mead algorithm. And this work was supported by CNPq and CAPS. It started when we have a cooperation with CAPS FCT some years ago. Thank you for your attention.
Thank you, Nilson.